Okay, good morning. It looks like we have our attendees starting to join. We wanted to just say good morning and welcome you to our third webinar of the year. Today we're focusing on building decarbonization in solar air heating. Before we start, I just wanted to give a shout out to the chapter's sponsors. Of course, a chapter like ours is able to offer programming like this when you have a pretty strong stable of corporate support. So this is just our opportunity to give them a shout out and applaud them for supporting energy efficiency throughout our chapter's territory. Of course, we are a part of a larger organization. The AEE Canada East is a chapter member of the Association of Energy Engineers, which is a fantastic global organization. Of course, their model is we are local, we are global, we are AEE. It sounds kind of corny, but when you've been around them for a while, you start to recognize the significance of that statement. So the chapter network is really the local aspect of the AEE's reach. And it is what connects the practitioners to the activities of the large organization. If you're not a member, we would encourage you to consider it. There's lots of resources available to you once you become a member, and I can tell you personally that I found it quite valuable over the years. Just a quick little piece of housekeeping. Normally in a situation where we've got in-person attendance, we would tell you where the fire exits are and where the washrooms are. Of course, we don't have to do that for you because you're sitting in your office or at home, but there is some housekeeping. So webinars are a bit tricky when it comes to having conversations. So we would encourage you to post your questions using the Q&A button in the Zoom control menu. And by posting those questions, we'll be able to moderate them and get them to the speakers throughout the presentation. And we encourage you to do that at any time. We find it works best. It at least drives some type of a conversation between the speakers and yourselves, even though there has to be a go-between. So I'm going to pass it off to Mark Bassini. He's going to introduce the speakers for the day.
Thanks, Andrew. So today we have SolarWall, and we have Todd Marin and Andrew Young. I'll pull up their bios here. Andrew's an avid proponent of ecological stewardship and decarbonization. He's responsible for national sales in North America for SolarWall engineering. Across many verticals, from multi-residential to military, he's been involved in many notable projects for SolarWall, including the first zero carbon building design certified building in Canada, the Evolve 1 building in Waterloo. And Todd Marin. Todd Marin's body of work is among the world leaders of solar air heating, overseeing hundreds of projects across North America and abroad. His extensive experience in product and project development, and is an active voice in the development and modification of clean heating governmental policy across multiple jurisdictions. I've personally done quite a bit of work with Todd and Andrew, so I can attest to all their qualifications. And today they're going to be talking about building decarbonization and solar air heating. So I will give the floor to Todd and Andrew.
Great, thanks very much. This is Todd here. What I'll do is I'm just going to share my screen, and you should in a moment be looking at a slide that says building decarbonization and solar air heating. I'll assume you're seeing it unless someone tells me otherwise. So thanks again for carving out a chunk of your morning to allow us to speak about SolarWall and solar air heating. Probably the easiest way to start off when it comes to solar air heating is to first say what it's not. So when people think of solar, they'll very often think of solar panels like PV panels that are designed to generate electricity. SolarWall is not that. Often people also think of solar energy as generating hot water. So you've got solar thermal panels where you've got solar energy that heats the thermal panel, and then usually it heats some sort of glycol loop, which then is converted into hot water. And our system doesn't do that. What SolarWall system is designed to do is one thing, and that's preheat ventilation air for buildings. So in what solar, again, to sort of restate it, and one thing I will say too is we run a sort of funny line at our company where our brand is called SolarWall and the technology is called solar air heating. However, in practice, almost everyone uses these terms synonymously. So you'll hear me say solar wall and solar air heating throughout this presentation interchangeably. So they mean the same thing. One's the brand, and that started it all off in the mid to late 1980s, which is the SolarWall brand, and solar air heating is the technology. So Andrew and I are representative of both the brand and the tech, if that makes sense. So yeah, the technology was developed in the mid to late 80s. And over the interceding years, across the decades, we've now got projects in 43 countries on every continent, including Antarctica. And with regards to the types of clients that typically engage with SolarWall or solar air heating technology, you've got your sort of who's who of your Fortune 500, Fortune 100, et cetera. The US military is the largest customer, just by the sheer volume of building stock. So for instance, as an idea of scale, at one base in Fort Drum, which is upstate New York, just kind of south of Kingston or so, they've got 56 solar walls just on that one base. And then in New Cumberland, Pennsylvania, there's 103 solar walls just on that one base. And across the military, the US military, there's about 40 to 45 bases, if you include the domestic stuff and, abroad, Germany, South Korea, et cetera. All of the major auto manufacturers have got at least one solar wall on their portfolio of buildings somewhere. And the reason why the technology has the popularity is we've got a pretty big problem that we aim to solve. So keeping in mind that SolarWall is designed to preheat ventilation air for buildings, if you look at the GHG impact on your building, that's a big energy hog. That's space heating, and specifically the ventilation space heating. So if you think of, say, a factory with some welding or something going on, you might have 3 air changes an hour, maybe even more. So if you've got 3 air changes an hour, you got to reheat that entire building every 20 minutes. So if we're able to carve out 20, 22, 25% of that ventilation heating load, it's a very big percentage of the overall impact on that building. Further to that, another reason why there's a growing popularity is the fact that the buildings that are here today are really still going to be here. So whatever the government target might be or corporate target might be, hey, by 2030, we're going to reduce by this amount, by 2050, by this amount. The fact of the matter is that the vast majority of the building stock will still be in existence. So there's a tremendous amount of focus on decarbonizing the existing building stock, because if you don't do that, there's just no chance that any of these goals are going to get achieved. So when you think of decarbonizing, obviously the big one on these days is looking to electrify heating, which seems a pretty insurmountable task unless you go back in history and look at the history of how we've been heating our buildings. So from time sort of immemorial, folks were heating their buildings with wood and very often animal, what do you call it, products, basically animal dung. So you'd burn your animal products and your wood, and that's how you'd get your heat for your building up until somewhere around the mid 1800s, when of course coal came online, and for a good chunk of 50 years or so, coal was the heating fuel of choice. And then another 50 years later, coal switched over to heating oil. Move forward another 50 years or so, heating oil transitions to natural gas. And now we're in the period where we're transitioning to electricity. So though it seems an insurmountable goal and something that, kind of air quotes, cannot be achieved, Well, the fact of the matter is our heating makeup has changed every 50 years or so, and this is just a continuation of the existing cycle. When you look to Canada, of course, it's going to be a little bit slower to adopt into that electric heating. If you're down in Atlanta or St. Louis, well, maybe it's not such a big impact from a cost perspective on electrifying your heating simply because of the short heating season. But in Canada, we've got a whole different picture up here. So electrification is a lot more, has come online a lot more slowly up here, but it's definitely coming. And SolarWall has definitely got a significant game to play in that, because again, if you're looking at a ventilation, any sort of building with any kind of ventilation demand, if you're able to knock off 20-some% of that load, of that demand, now all of a sudden the cost or the difficulty in electrifying that heating has been reduced by an equivalent amount or equivalent percentage. Something that is kind of a bulky slide that might take a second to look at, but one thing that's not intuitive at all is when you think of solar panels, as in solar electric PV panels, one of the great narratives that drove the uptake of solar PV for the past decade or so, and we've all seen the dramatic adoption of solar PV over that period. And one of the main drivers of that is peak electrical demand was a big issue for the utilities. So you've got that super hot day in August when everyone's air conditioners turned up to, full blast. And that just so happens to coincide perfectly with when a solar PV panel is generating its highest output, because typically that's a sunny, hot day. And so this nice correlation between that peak energy load really assisted the utilities in maintaining the electrical grid, because they didn't have to have all this unused capacity sitting around, because you had the PV to help you specifically when you needed it. Well, it's not exactly intuitive to imagine that on the coldest days of the year, you have a similar high solar energy demand, but the truth, or energy production, but the truth of the matter is that is the case. So what happens is when it's super, super cold outside, is the air is just not able to hold the humidity. So there's a real correlation between very cold days and very clear days. So what we did is we just did a quick little study in a few different jurisdictions. We pulled a few weather files, and I'm sharing here the results for the city of Toronto, just Pearson Airport weather data. We took the top 5 demand days for each year over the past decade. So each year we took the 5 coldest days, assumed those to be the highest demand days for natural gas, and then looked at that across for a decade worth of days. So 50 days, five days a year for 10 years is 50 days. Of those 50 days, 47 of them had above average solar radiation. So only 3 were below average. And the average above average solar radiation for those periods was 141% of typical. So there is a very real correlation between the solar production on a very, very cold day and the performance of a solar air heating system. Now the question is, why does this matter? Does the natural gas grid have the same types of constraints that the electrical grid might experience on a peak day? And the answer is an overwhelming yes. We just haven't quite seen it yet up here in Canada, perhaps a little bit on the most easternmost part. But in the Northeast United States, they are completely out of gas. So for instance, in Westchester County, which is just north of the city of New York, you're not allowed to have new gas hookups. And there's a lot of other jurisdictions, because that trunk main supply line, regional supply line is at capacity. And as you might imagine, the gas utilities have no interest in upgrading that trunk supply when they're simultaneously trying to electrify, because they've got this stranded investment. So it's a tremendous opportunity for energy efficiency technologies to react to this low, this kind of natural gas threshold. And Andrew, you can jump in here and get into the specifics of what the heck a SolarWall is and how it works.
Okay, great. Thanks, Todd. Hi, everyone. So this slide here is just here to explain how does the SolarWall actually work. So as Todd mentioned, the SolarWall is essentially, it's a micro perforated metal wall system designed to preheat your ventilation air. So as you see here, that you've got a building, and then I don't have my mouse on here. Todd, if you want to sort of use your mouse. So you have the solar wall collector surface, which is that red dotted line, and that is going to be on the exterior of the wall, either a south or east or west facing wall. And then what we're going to do is at the top there, we are going to, in this example anyways, run an insulated ducting to the intake of that air handler or the makeup air unit of the building. So essentially it's everything behind that solar wall collector surface is an air plenum. So what we're going to do then is, of course, we're going to use that solar gain that we get on that wall, and it's really the boundary layer of the solar wall surface that we're collecting that heat from. If you were to touch a wall like I did yesterday, and a nice black wall, and it's pretty hot, the further away you go, the less hot it is. So what we're doing is we've designed our system, and each system is custom designed to capture as much heat from that wall surface, the total wall surface, as possible, so that we are obviously getting the most efficiency out of the system as well. The other thing to note is we're not just getting heat from the surface of that wall. Like most buildings, depending on the R value of the wall, there will be heat loss associated. So what we're actually going to also accomplish is recapturing any heat loss from the building wall where the solar wall is located. And then we're just going to bring that right back into the building. So essentially now the solar wall, the entire surface during the heating season, is the intake for your HVAC system. So we're going to collect that solar gain from the surface. We're going to bring it into the building, and we're essentially piggybacking on the fan that is already existing in the HVAC system. So the solar wall itself, the solar wall system, it's really a passive system. I call it a passive active system because it's just the active parts sort of we're attaching to that active part. And then the air is going to heat up further through the HVAC system and distribute it into the building the way that it would normally. Now, in the summertime, obviously that solar heated air is not wanted in the building. So we have bypass dampers installed in the ducting so that it's going to close off the solar wall system, open up the bypass, and now your HVAC system is going to work as though the solar wall isn't even there. The nice thing about the solar wall in the summertime is that now you don't have that direct solar gain on the actual wall itself. The solar collector surface is sort of blocking that, and because it is micro perforated from the bottom up all the way through, and using the stack effect, essentially it becomes a self-ventilating wall as well.
Andrew, I've got a question for you.
Yeah.
You're saying earlier that that your system piggybacks off of the air handler's fans.
Yes.
Have you come into situations where you've had to upgrade those fans? Like, is the static pressure issue?
Great. Great question. So the static pressure off the solar wall itself is it's 3/8 of an inch of static pressure that is added to the system from the back of the solar wall system itself. Most of the time, it's such a minimal added static that there's nothing really needs to be done to the system. However, in buildings where maybe there's a very old HVAC system, a booster fan might need to be incorporated into the design. And we also have a two-stage system as well that adds a little bit more static pressure. But again, I think that's only just slightly more. In this slide here, this is sort of also indicating how well the solar wall works. So I just sort of briefly went over how, in that example anyways, the solar wall is installed on the building itself. And keeping in mind, it is a building integrated system, so it has it just will look like a metal cladding on your building. So this slide here is showing one of our two-stage solar air heating systems. Essentially, it's preheating the air twice. And what this chart is showing here is that the blue line is indicating what the ambient temperature is outside in Fahrenheit. And this example is actually down in New York State at Plattsburgh Airport. And then, of course, the yellow line is indicating the SolarWall temperature as the day progresses. So that whole range in between the yellow and the blue is essentially the added benefit and heat gain from the SolarWall versus not having any solar air heating for your building. And then the nice thing about the solar air heating system too is because there's no energy conversion. We're just taking hot air and moving it from one place to another. The efficiency of that system is also tremendous, upwards of 80-ish%. This performance data as well is just additional data from the chart that we just saw, just to give you an idea of really the heat that a solar air heating system can provide a building. So in this particular example, on a normal sunny day outside, the temperature rise has almost been 110 degrees Fahrenheit, which is a pretty significant temperature rise to achieve. And in doing so, of course, we're really offsetting a significant amount of the heating fuel. And as Todd was mentioning, in most cases, that is natural gas and has a significant carbon footprint associated to it. So where can solar air heating be used? Really, it can be used anywhere that heat is needed for a building. We do a significant amount of ventilation air preheating. However, we also do quite a bit of process air heating as well. So in anywhere from industrial, commercial, institutional, hospital, schools, we do a ton of multifamily, agricultural. So in the next few slides, there's just a couple of examples of some of these verticals in which we work with. So in this slide here, we're seeing some industrial facilities. The first one there is Owens Corning in Ontario. And as you can see, it's a pretty clear indication of where the SolarWall is on that building. And the following year, actually, it worked so well for them that the sidewall that you can see in this photo, the following year, they added an additional SolarWall to that wall system. Number 3 down in the bottom corner there is a Bombardier assembly facility in Quebec. Now, this is the largest solar air heated system in Canada. It's over like 100,000 square feet. They manufacture planes, so it's definitely a really sizable building there. So the other thing to consider when considering a solar air heating system is that essentially it is, other than our custom design and engineering, it really is a metal cladding system. So we have a range of different profiles, colors that you can sort of work with. In image 2 there, you see it's designed on a curved wall. So really any aspect of a metal wall design, a solar air heated system can also be designed in this much the same way. In image 3 there in Germany, you see that the floor slab detail on the building, they wanted to remain consistent throughout the design. So they added that element into that solar air heating system. And again, it works just the same as if that detail wasn't there. Schools and universities, we've done hundreds of schools and universities across North America. These are great projects to work on because first off, ventilation is obviously a very important aspect in schools and education, but they're also a place of, education, of learning, exploration. And when you can actually look at the wall and say, this is actually not just a normal wall, this is doing something significant for our building, reducing our carbon emissions. It's a great sort of talking point for principals, for teachers, for students, as well as being able to gather, data off it. We have a facility in Fanshawe College in London, Ontario, and they're doing some really wonderful things in terms of using that as an example to teach in some of their programs. Institutional buildings, of course, rec centers, wastewater facilities. Number one there is just, it shows how it's again, it looks from the exterior, it looks just like a normal metal cladding system. So we can design it to just sort of fit into the building, however it would benefit that building's aesthetics. And number 3 down there is at the National Renewable Energy Laboratory in Colorado. And we've got about like 3 systems on that building, which is quite sizable. So we can go around windows and part of the custom design element of this type of system is that we do have that ability to work with whatever wall, south, east, west wall that we're facing, and however it needs to be. So,
Hey Andrew, just a quick question from the panel, from the folks in the audience. Do you have examples of where a solar wall has been deployed on an ice rink in Canada, and then do you have any information on what the performance of the heating system was with or without the solar wall?
Yes, actually, a recent installation in Ottawa on the Blackburn Arena. We have a solar wall system installed on that south wall. I don't have any data for that yet. It was just recently installed. That's just the one that comes on the top of my head. It was actually one of the first projects that I worked on with solar wall, and it's sometimes it takes a little while for these projects to actually get implemented. But that solar wall system is preheating the ventilation air for the change rooms in that specific example. In terms of how well it works, it works. I mean, we have our energy model that determines sort of the feasibility of what it is likely to achieve. So it's going to achieve essentially something very similar to what the solar wall would on many other buildings. With that,
I'll jump into Todd here. Is on an arena, the challenge would be the set point, right? So as you might imagine, if your set point is 40 F or some 5 degrees C, there's going to be fewer hours where you're going to want that solar heated air, potentially on an arena. So from a solar wall perspective, if you kind of step it back and look at it from the way we would approach it, the building itself is reduced to basically what's the ventilation demand, what's the schedule, and what's the set point. That's kind of how solar wall looks at a building. So for an arena, it could be such that if you're feeding the area where the ice is, we just have such a low set point that so many of the BTUs that we're going to create aren't going to be put into the building. So we would understand precisely what that was during the project development. We produce the energy model reflecting that schedule, and then you'd know precisely what the impact would be. And then just a little further along in the slide, I'll kind of show you how we sort of prove it up front. And then the second thing I will say is very often an arena will also have other areas that aren't ice, right? So you'll have common areas, you'll have, maybe there's like a running track up above where it's a set point's like 18C, or you've got a multiplex with some sort of, couple gyms and volleyball courts, et cetera. And we would feed those common areas, lobbies, et cetera. So we get on a lot of these multiplex type projects, but if you're just feeding a rink, we would need to look very, very hard at the set point and make sure that we weren't over representing the hours in the energy model. And then we would know precisely what the impact would be.
Yeah, exactly. The Blackburn Arena, that was more of a specific arena project. And then as Todd was mentioning, down in Minnesota, we're working on a project. It's going to be installed now, which has more of a running track and a larger sort of a example. So for the multi-family buildings, again, this is another one where we've seen a significant amount of interest in, because of course, a lot of the time for these buildings, there's a makeup air unit on the roof, which feeds the hallways and the common areas, and that's running all the time. What we're also noticing more and more these days, especially when it comes to energy efficiencies of these types of buildings, is a lot of the time people are building operators and owners are sort of recladding their buildings, and that is also another excellent time to look at solar air heating, because again, we essentially will be we're cladding as well. So it's a great opportunity to investigate whether the solar air heating system will be suitable for the building that you're considering.
Andrew, I have another question here. I have my own rules of thumb, but I'll let you answer this. If someone's trying to determine a high level, opportunity analysis on SolarWall, and they're just looking for some rules of thumb in terms of equivalent kilowatt hours per year per square foot or square meter of installed surface area, do you have any rules of thumb for that?
So for our system, it's kind of difficult because we're so custom, because every building is going to have their own parameters. What we typically will do is, if there's a building that is of interest, or somebody's looking at me like, maybe solar air heating could be an opportunity for this building, what we would do is just sort of on the slide say, get in contact with us, call, email, don't be shy, and we'll work with the data that you've collected on the building, the CFM of the units that we're looking at. That's a very key measure for us. Also, something to consider with the SolarWall is we do have sort of a parameter in which we can work within. So the SolarWall system itself works effectively from 1 CFM per square foot of SolarWall collector surface to 10 CFM of SolarWall collector surface. So there's some limitations as to how the sizing of the system. But when it comes to if somebody's interested in a building and they want something sort of, some information sort of quick, hey, is this a good building? We are able to sort of quickly look at the building and give you an answer, especially a high level answer, quite quickly. We might just need just a couple pieces of information, but usually just maybe within that, that day, we can get you at least some high level information, and then maybe just give us a couple days if you want us to, prepare, of course, like a budgetary proposal, as this slide is indicating, and we're happy to do that as well. And what that budgetary summary will include is, of course, the preliminary design of the system, how it's going to look, what system we would suggest for the application, how we would integrate that into the mechanical system, of course, including all the project costs, any energy, all energy savings, of course, resulting financial information as well, paybacks, ROIs, that sort of thing. And of course, most importantly, in my perspective, is also the carbon and GHG offset analysis, and how much we're actually able to reduce for that building. Of course, it's a sizable metric these days, and I think over the next decade is going to continue to be a sizable metric that people consider when looking at their buildings and how to upgrade.
So I'll just jump in here and grab the reins. Again, so just to summarize the benefits, basically solar air heating, the nice thing about it is it's very, very predictable. And further to that question about the rules of thumb, as long as we know just a very, very small number of variables, we'll be able to very accurately predict what the savings will be. Keeping in mind that the system's been around for 30 some years. So it's there's not a lot of guesswork. There's a lot of field data. There's a lot of M&B reports that have been produced of varying degrees of quality, but certainly consistency across the center. And there's certifications, et cetera, which I will go into here that reflect the test data and make it very easy to quantify and any energy model. So with respect to rule of thumb, all we really need to know is what's the airflow? What's the schedule of that airflow? What's the set point of the building, i.e. are there hours we're going to cut out? And what's the area available for the solar wall system? What's the azimuth, so the orientation towards south of that particular wall area. That's all we need. We can do a really good energy model, costing and everything, and we do that all day long. So like Andrew had said, don't hesitate to reach out to the two of us at any time, and we'll just run the numbers for you. It's what we do all day. The beauty of solar wall as well is getting to scale is really what's important. So we're seeing a lot of folks like let's say an industrial REIT that might own 180 industrial buildings. Industrial buildings, of course, are nice for us because of the ventilation demand is often high. So we're able to very quickly analyze, produce energy models, and then manufacturing and installation is all very, very easy because the trades, if you look at that construction picture there, that trade that's building that solar wall, it's basically just the same thing as a regular old metal wall with respect to what's involved in the installation. So getting to scale is easy because it's not a very specialized type of labor, meaning you don't necessarily have to go with a crew that's experienced in solar wall. I mean, finding one might help on the initial price, but as it gets to scale, the cost of installation it's very competitive, so the pricing stays low. As far as maintenance on the system, none. So we're hitching a free ride on that existing ventilation system. There are some instances where we'd introduce new fans, like Andrew had mentioned, sometimes to make up static, even though 3/8 of an inch is usually fine for almost every system. But if you have a super long duct run or something, it might require that. But also for example, we do a lot of airplane hangars and these types of big buildings for military, where often we'll just use a standalone fan to bring the air in as opposed to integrating with a mechanical. And then the big one, of course, is carbon. So when you're chopping out 20 or so % of your ventilation heating demand, that's a significant amount of carbon, particularly given the fact that a solar wall sits there and does its magic for 40 years. So it's got a 40-year life cycle. There's no degradation. And the life cycle carbon offset's usually somewhere around 5 tons CO2 per square meter.
Oh, Todd, we've got a question here about whether solar air heating can do all of the heating of the building. Do you want to?
Yeah.
Do you want me to?
So no, that's the answer. So typically, it's a good question. And typically what we do is we sort of insist that you look at the solar wall system as an add-on that's going to offset the fuel consumption associated with ventilation heating. And that's it. So if you're looking to reduce your capital expenditure, like downgrade a burner size, unfortunately, you can't do that because a solar wall will necessarily, you have to assume zero production because there will be days when sun's not out, and certainly at night, there won't be any sun. So you can't reduce capital costs, but with respect to your heating system. However, as Andrew touched upon, in many contexts, such as every single new building, solar wall is not just an energy system, it's also a cladding. So it's a wall, not just a heating system. So you take out the cost of whatever planned wall would be, put in the solar wall cost, there's a tremendous amount of capital expenditure efficiency there. And then also on a lot of these overclad buildings, if you're putting, say, an EEFS or EEFS system on, or some sort of cladding for some degraded brick, the cost of a solar wall and the cost of an EEFS system is about the same. So you kind of get a free solar wall if you bring it in to an EEFS install.
Hey, Todd, while you're chatting, you had mentioned a few minutes ago about some more of the applications where you've seen the wall deployed. Do you guys have any situations where like a bank, an institution, a financial institution has put a solar wall on their building?
A bank specifically, we've done so many institutional buildings, but I guess, yeah, I mean, I guess a bank we probably define that as commercial. But I don't think we've ever done a bank. We've done a lot of courthouses. We've done a lot of like office buildings that maybe there's a bank in one of them, but not a specific bank. One of the things that is interesting about our system is there's a lot of colors available. So for us to match, say, like a CIBC maroon or whatever that color is, we can definitely do that. So we often will do like sometimes I'll call that corporate trade dress. You know, they got to build a building, it's got to be that color. But specifically a bank, I don't think so, but there's nothing that would make it, you know, it's just a commercial building from our perspective. Often the ventilation demand is not particularly high in that type of facility just because of the occupancy, but we could definitely run the numbers based on the schedule. I'll just quickly touch on the SRCC standard. So SRCC is the governing standard. There used to be a CSA certification for solar air heating, but then the SRCC was the American standard. It's a little bit better. And so we worked with, we sort of replaced CSA with SRCC North America wide. There's in Europe, there's Keymark. In Asia, there's other ones, which I can't recall exactly right now. But this is important to understand because it really reflects the test data for our system. So when you look at it, it's a bit of a mess. So I'll dig in a little bit deeper here to get to the real meat of it. So if you look at this section here, you'll see that there's so this is test data from the National Solar Test Facility in Oakville, Ontario. And right here, you'll see that the various airflow rates at which the system was tested. And then here you'll see the wind speed. So as you might imagine, on a really, really windy day, you're going to get less production than on a not windy day for a solar air heating system, because that wind will kind of shear some of the heat away from the system. So at different wind speeds, you've got different productions. And then, so if you kind of zoom in here, you'll see 2 CFM per square foot, 4 CFM per square foot, 7 CFM per square foot. These are the test standards. We got the different wind speeds. So if we kind of focus on the center column, you know, medium wind, you'll see that there's an efficiency rating right there. So this is the efficiency of the solar wall system. So you take the solar energy landing on that vertical plane, keeping in mind that we're on a 90-degree angle, right? Which, if that was PV panels, that would be no good, because all July, all August, all June, you wouldn't get the sun because it's so high up. But keep in mind that a solar wall system, we don't care about summer. We only want the winter production, because during summer, you're not heating your building. So on the vertical, you actually get really good production in the winter months, much, much better than, say, a 30-degree angle of a PV panel. So there's your efficiency, and it's very, very simple. You take the watts per square meter on that vertical plane, and then you multiply it by that efficiency, and now you've got your solar production. Simple as that. So just to summarize here, each airflow's got its efficiency value. There's that range that Andrew mentioned, 1 CFM per square foot to 10 CFM per square foot. So it's a pretty wide range, and that's why a solar wall system is always custom engineered specific to the application, because assuming that the airflow required by the building is a constant and has nothing to do with the solar wall, it just has to do with what the building demands, we will customize our system to accommodate that airflow. And if you look at 1 CFM to 10 CFM per square foot, we can build a solar wall either one size or 10 times that size for the same amount of airflow. What you will notice, and this is not exactly intuitive, is that the higher the airflow, so the faster the air is moving through the solar wall, the better the efficiency, which is what almost, well, it is the exact opposite of what people will very often think. People will often think, well, the slower the air goes, the more temperature you'll gain because it's stewing around and collecting heat behind that panel. But it's actually the opposite. So what happens is when you think of the sun striking a surface, the vast majority of the heat doesn't go behind that surface. It's actually on top of that surface. So we call that like the boundary layer of heat. So if you walk out to your car on a sunny day in June and put your hand about an inch above the hood, there'll be this boundary layer of super hot air. And then if you go like 3 inches above, you won't feel, it'll just be ambient temperature. So what a solar wall is designed to do is take that boundary layer of heat and bring that into the building. So it's actually much colder behind the wall than it is than that heat we just took. So the design goal is to get into the building as fast as possible as opposed to stew around and gain heat. So that's why you get that better efficiency at the higher airflows. However, often a lower airflow system, though it has a lower technical efficiency, actually has a better financial efficiency. And that usually is a result of the fact that if you assume the airflow is a constant, you've got the costs associated with ducting to the air handler. You've got the costs associated with kind of engineering, getting a lift on site, all these fixed costs. And then the solar wall itself is an incremental cost. So each square foot of solar wall is a relatively low percentage of cost overall on the project. So the larger the wall, the better the relationship between that incremental solar wall cost versus the fixed costs, having to do with engineering and setting up on site. So very often, even though the system's got a slightly lower efficiency, the financial equation is much better. And of course, the larger the solar wall, the lower the airflow through the system, but also the more GHGs offset. So that sort of falls back to Andrew's comment with respect to rules of thumb. The easiest thing to do is just get us on the phone, give us the details, and we'll customize the system best for you.
Hey Todd, have you guys ever found any solar heat gain reduction in the summer months because the solar wall has been installed on a building? Have you guys measured that or seen
Yeah,
it?
so many moons ago there was a modeling software called Swift. So there was a little bit of a battle between what would be the standard for modeling solar air heating, and it was RedScreen versus Swift. And this is like 1997 stuff, right? And RedScreen ended up sort of winning, or not winning. Swift just kind of abandoned it after a while. It wasn't quite as effective. What Swift did was it quantified the summer cooling benefit of the solar wall. So like Andrew had mentioned, the solar wall is this giant metal collector, completely sealed around the perimeter, and it's got 200 perforations per square foot. So it's basically a sunshade all summer long for that south wall. Swift used to quantify it, and it would somewhere arrive in like the overall production was about 2% of the savings was a result of the cooling load alleviation. To be candid, as an engineering company, we didn't really, it was hard for us to trust that number because we knew the number of variables that went into it, and it's a little bit more of a full building audit to quantify it. So we know that it's better in summer than without a solar wall. And anecdotal evidence, a client of ours once said he had just a basic metal building wall with a solar wall on the outside. And he said when he slid his hand along the inside of the wall in the summer, he could feel where the solar wall started because it was much cooler than the other wall, or the wall adjacent to the solar wall. But in our energy models, we always quantify it as a zero, understanding that it's a net benefit, but it's within the context of our energy model, it's difficult to quantify it specifically. So we just say it's good. We don't know how good, but it's definitely better than not, if that makes sense. And then almost on these slides, just quickly dive into the M&V, what's required to measure it. So in a theoretical sense, it's very, very simple to perform measurement and verification of a solar wall system. So basically you need to measure a couple things. One is outside air temperature, fairly straightforward. Again, theoretically, I've seen it been done wrong a lot of times. Measure its solar wall temperature. So basically you take the outside air temperature, then you take the temperature produced by the solar wall. So if you imagine all those BTUs hitting that huge wall, which might be, 9,000 square feet in size, fundamentally all those BTUs get squeezed into a duct at some point that goes into the ventilation system for the building. So the best point at which to measure that temperature is within that duct. So you measure the produced temperature, you measure the ambient air temperature, subtracting one from the other, you end up with a delta, and that's the the temperature that the solar wall is producing above ambient. Then all you need to do is cross that with the CFM of fresh air, or CFM of air being pulled into that air handler, and you've got a BTU. So outside air temperature, solar wall produced temperature, the CFM, and then you're able to calculate the BTUs generated. Then it's important to understand that if we're dealing with natural gas, a lot of the time, those burners within the natural gas system, they're not 100% efficient. So you would have to divide that by the efficiency value of that system. So if you got an 82% efficient burner, you make an estimate on that, and then you divide that BTU. So the generated number is the offset system. The offset numbers are higher than that generated number because of that efficiency of the burner system. And then as kind of a diagrammatic representation of it, one of the challenges that we've experienced is accurate measurement of airflow in the field. So we found that there's been a tremendous amount of sensitivity to the installation, depending on what kind of air measurement device is used. And of course, there's always cost associated with it. So you can spend a lot of money on a very complex air measurement device, but then the danger is it ends up getting value engineered out of the project at some point if it's too expensive. So what we've done is we've sort of standardized our M&V in the sense that we try to eliminate the necessity for an actual airflow measurement, and instead we rely on a test adjustment and balance report, like a tab report at project commissioning, to substitute for point measurement of that CFM. So you end up with a result where you can hard code the CFM value based off a tab report, as opposed to field measurement of that airflow. So in a perfect world, we'd like to find a non-installation sensitive, something that the installer can mess up, because we all know the installer will, and that we can use in field to accurately measure airflow, and that would alleviate the need for us to base it off the tab report and get at a better number. But currently, what we've worked with is the standards that are being propagated by, in this case, I'm showing the M&V protocol from the state of Massachusetts Department of Energy Resources. What we have here is you've basically got the solar wall collector, which they're calling a transpired solar air heating collector, which is another technical term that's used for it. Basically, you're just recording that temperature delta. You're recording the solar damper position. So is it in summertime bypass or is it not? Obviously, if the system's bypassing for summer, you don't count those BTUs because they're not being consumed by the building. And then very often you've got some sort of mixed air within that unit. So you've got recirculating air coming in and out of the unit, and that's controlled by a damper position. So we need to tie a signal to that damper position, and that signal needs to correlate to a tab report. So when you're producing the test adjustment and balance report at commissioning, you need to do it at every single damper position. So 0 through 10 on that mixed air damper, so that you're always quantifying the precise amount of fresh air coming into the system. And so now when you've hard coded a CFM value to each damper position for the return air or mixed air, again, if that's present in a high-rise multi-res building, there just simply isn't mixed air, it's just 100% fresh, or many other buildings, then you're able to achieve that CFM value. That's hard coded, and in it goes. And then of course you would mathematically divide by an assumed efficiency of that ventilation unit. And this will be the last slide. Basically, it's nice to look at closeout submittals just to make sure that you wrap your hands around all the elements of what a SolarWall system is. And again, it's very, very simple. So you'll see the submittals are pretty straightforward. Ultimately, when a project goes forward, there's a set of shop drawings produced by the manufacturer, i.e. us, and there's a structural stamp on those drawings. You need to sign off on that structural engineer. Mechanical. So mechanical for SolarWall is basically the wall gets built, and then you've got to somehow get a duct or a few ducts, depending on how many units there are, over to the air handler, which then feeds the air into the building. So you need to sign off on that mechanical stamp. And then again, that tab report, you just want to make sure that the system's doing what it should be doing. And that's very important, not necessarily for the SolarWall, but often those units aren't doing what the label says. So it's always important to make sure you do that tab report to make sure that indeed the ventilation air is coming in to the degree to which you think it will. And then that's able to verify and quantify the energy model. And then you know the numbers are good. And that's a wrap.
Hey Todd, there was one more technical question. If you have a few seconds before we close off.
Okay.
So the question was how do you control the differential pressure in the building with the SolarWall? And I think I know the answer to this, but I was hoping you guys might throw it out there.
How do you control the differential pressure in the building? So I guess I need a little more. What do you mean on that?
I think the question is, by putting the SolarWall into the system, do you impact the differential pressure of the building, the mechanical systems of the building, or do they operate kind of as they always have?
So our design goal is to integrate as easily as possible. If you can imagine from our perspective, the easier it is to stick a SolarWall in the building, the higher likelihood one will do so. So with respect to the mechanical, we're going to add 5/8 of an inch of static, or 3/8 of an inch of static at the SolarWall panel, and then whatever the ducting would be. So there's going to be that much static pressure added to the system. So typically we look at that as fan consumption cost. So somewhere in the neighborhood of 60, 70, maybe $100 if it's a super high flow system, like a big air handler. You're looking at that kind of added electrical cost just based upon that static alone. So that's not 3/8 of an inch. I'm just kind of bumping it up to what a typical ducting would be. So we will perform a tab report to make sure the building's doing what it needs to do. Sometimes you need to change a shiv on an air handler so that it's running as it was before. But our goal is for the design condition with the SolarWall to be identical to the design condition afterward.
Sorry, there's also oftentimes where a building might have like negative pressure issues already associated with the building. By adding a SolarWall or a solar air heated system to that building, we can help balance that, because now all of a sudden maybe it's a little bit more cost effective to bring in more air into the building that is being exhausted maybe more significantly than just leaving dock doors open or getting the air to come in through any leaks in the building. So there has been times when the SolarWall added to a building has helped alleviate those sort of issues.
Yeah, I know Armstrong's one of your sponsors, and they on their facility in Scarborough, they had one of these old buildings where they kept adding exhaust, but they weren't matching it up with intake air. So you had this tremendous negative pressure, and so every time like the UPS guy would show up, the place was freezing because the air would just gush in, right? So, and if you happen to be the unfortunate guy located near that little crack in the wall or whatever that no one knew about, you were cold all day and the guy next to you wasn't. So what we did in that case is we introduced fans, like we introduced intake air into that building to balance it out, and then just sort of slightly positively pressurize that building. You could really tell because opening the door to the warehouse was markedly different when the SolarWall was running and when it wasn't, just with the suction, right? And so that's something that is very often done, particularly with these old buildings where they've, used to just be welded there and died at 40, You know what I mean? Back in the old days, and then now they kept introducing exhaust, but now we can balance the building out. Nice.
That's awesome. There's actually a really interesting question here that I hadn't thought of before, but have you guys ever paired a solar wall deployment with some sort of thermal energy storage so that you could potentially get the benefits of a solar wall at night?
Yeah, we've played with it a lot. I guess it would really be what we've arrived at is a couple things. So yes, it theoretically works. It doesn't necessarily pencil out from a cost perspective. So we got 6,000 pounds of phase change material in our office that we walk past, when we got to go back to the warehouse to pick something up. When Andrew borrows a drill for one of his many home improvement projects. So what we've done is we've looked at incorporating phase change into the system. So now you get this sort of like sunset system where the sun goes down, but you're still producing solar heat. What we found is a couple things. The efficiency of the storage, there's a little bit of an efficiency fall off just necessarily by physics. And that coupled with the fact that almost always when we do our buildings, we're immediately consumed. So we're not really overproducing, if that makes sense. If a building is such that they don't really want our heat, then we just kind of do the next building, if that makes sense, as opposed to get that building. It does make sense theoretically, and we've done it. We poured it through gravel beds. We've tried to put it into concrete, and we've used phase change. But at the end of the day, we found that the benefits usually don't, they just don't pencil out from a financial perspective. But it's a great question because, yeah, we've been working on it, trying to figure out a way to offer it.
I wonder, does that equation change with an escalating carbon tax, potentially?
Yes, except with respect to building selection, there's so many buildings where we would be consumed immediately all the time, and the heat's always welcome, if that makes sense. Like even an apartment building where we're pulling in fresh air, and we can produce some pretty big temperature deltas, like above the set point of the ventilation system. But let's say it's, February 5th, and you're in the hallway waiting for the elevator, you don't mind if it's slightly above set point in that hallway. And then the air itself, if you look at the airflow in an apartment, it goes underneath the doorways into the units and offsets, say, an electric baseboard heating or some other heating system within the building. So those BTUs are almost always instantaneously welcome in the building. So there's not really a benefit of the storage, if that makes sense. Now, we could always oversize the system like crazy in order to store it and have it run all night, which again works in theory, but then we'll run into situations where we've got a very low flow of air relative to the size of the solar wall, and it just, the math starts to break down a little bit.
Awesome. Well, it certainly is an interesting angle to take. I mean, we see people starting to look at energy storage, thermal or otherwise, and so obviously they're gonna look at your system and think, hey, how does this fit into the ecosystem of energy storage? So happy to hear that you've looked at it at any rate.
Yeah, one of the applications where it can work quite well, although it hasn't really been employed, is agricultural crop drying. So if you think of like drying apricots, for instance, if you come in at 55 C, you're drying the apricots. If you come in at 60 C, you're cooking the apricots. So there's a tremendous amount of sensitivity. So what we typically do is we design the system, we just go to bypass, like to balance that temperature. When we're overproducing, we just bring in ambient from a bypass damper. Conceivably, that could be offset by some sort of storage material. But even when you look at a phase change material, you need a lot of pounds of phase change to hold BTUs. You're looking at somewhere like 75 BTUs per pound. So we're dealing with millions of BTUs, right? So you end up with quite a few, you're looking at 8,000 pounds of phase change for a solar wall system. It's kind of difficult.
Yeah, but I wonder, and I'm just noodling here because this isn't my area of expertise, but like I wonder if you oversized your system and you started looking at the other heating requirements within a building. I mean, I know you're focused on ventilation air, and rightly so. I think that's the right approach, especially for a system like this. But if you had an opportunity to offset some of the other heating loads within the building, I wonder, like, have you considered that, or do you remain exclusive to ventilation in any of your analyses?
So, well, I mean, we can absolutely run the numbers specific to whatever the heating load is. Like we can definitely do it. I guess the keeping in mind that we're bringing in outside air, right? So we're bringing in outside air. Now we can do recirculation air, where you're taking inside air and running it through the panel and heating it, but then immediately you're cutting out a lot of hours because you have to be above set point, right? If it's -20 out and you're bringing in -10, well, you just save 10 degrees. But if it's a recirculating system, you would never even turn on, right? If it was -10. So we can definitely run the numbers for that. What would happen is when you have that much air and we're pulling in fresh air only, there's only so much fresh air a building wants. And if the building wants a whole bunch of fresh air, which means we can make the system huge, we're still in a similar equation where those BTUs are wanted immediately in the building. So we don't really have leftover BTUs unless we were to make standalone fans that are spinning specifically to feed the heat, like the heat storage, which again, it totally works. It's just the numbers don't jive all that well. I mean, if you look at it from a, hey, we've got a mission to shave as many tons of carbon as we can every single day, right? There's an unlimited supply of buildings that have a very high ventilation demand that need those BTUs, whereas the ROIs on that storage type is kind of difficult. Now, when you get into glycol and some of the higher temperature deltas, like with solar water heating type systems, you've got a lot more options, right? You can bank it and battery it a little bit differently. You run into some kind of like initial efficiency issues with those systems because they're about, a third of the efficiency of like a solar air heating system. But that's often a better bet when you've got something like a glycol, which you can put wherever you want real easy, as opposed to trying to bank it into some sort of concrete or water medium or something like that.
Awesome. Well, I guess the moral of the story is to keep it simple.
Kind of, yeah. I mean, we do our best to make it as complicated as we can. And the funny thing is, the system in 1986, when we stuck it on the big, huge Ford plant in Oakville, our system is the same as it was then. We're a bit smarter, on what to do, and we got a lot more certifications and M&B, and we know how to make everything happen. But most of the developments, they make tons of theoretical sense, but then they just don't pencil out because the ROI is great on a SolarWall.
Awesome.
Yeah.
All right, guys. Well, Andrew and Todd, thank you so much for coming and sharing the solar heating story with us this morning. I think there was a fair bit of interaction with the audience, which was great considering the medium that we're sharing it in. But I just wanted to thank you guys both for taking the time and talking to us and answering all of our questions, even though some of them sometimes perhaps were things you've heard before and just have to continue answering. I just want to let everybody know on the line that this is our last webinar for this session. The summer, well, school's out for summer, and so are we, I suppose you could say. We'll have some more webinars and a number of other events to look forward to in the fall. So watch your newsletter and watch the LinkedIn feed for anything that's coming up. But we'll wrap off for the day. Thanks for joining.